And I would like first to welcome the audience from around the world. I don't know in which countries, but we were used to have people from Africa, from Middle East, and also from the North America, and also other parts of the world. The conference, the e-conferences, started or launched by the joint venture between the ForestNet, the researcher of Morocco, and also the geology. We take the opportunity to express the motivation of the ForestNet first, which is gathering community of researchers in phosphates in Morocco and also in other countries. The idea was based on the existence of really a big network of researchers working on the phosphates, and based on that, we have also the OCP as a leader in the world in the industrial phosphates, and then the mission, let's say, of this ForestNet was really based on the promotion of R&D and also scientific production, and also to bring together really the mindset and different, let's say, researcher in this field. Now we have started to create synergies between really the university and different fields. Also, we have different partners in that sense. The e-conference, let's say, concept also now start to evolve, not only in the mine part or the mining, let's say, field, but also we have, let's say, now you can see from the past we have really different people talking from material science, chemistry, digitalizations. We have also recently talking about really astronomy and so on. And in that sense, today we have the pleasure to have our, let's say, guest speaker, Dr. Sandeep Surya. I will give really a brief introduction about his career. He was receiving his PhD degree from the IIT in Bombay in India in 2017. Now he is currently a researcher in the sensor lab in the King Abdullah University of Science and Technology. Prior to this, he was really a researcher associate in microsystems technology, technology research units in the Fondazione Bruno Kessler, Trento in Italy. And then his really research interests are focused on different parts related to microelectronics, chemicals and radiation sensors, memory devices, and also nano. Let's say interests. He was also, let's say, co-authored and authored, published different articles and also patents in diverse fields. And it's my pleasure to leave you the floor. I want just to mention before that I was in KAUST 2 times. I stayed in the campus for three months. I was visiting, let's say, the KCC Catalysis Center in KAUST, Professor Basset, and then I was also visiting the CRA, which is the Innovation Center of SABIC, for a few months. Thank you for being with us, and the floor is yours.
Thank you. Thank you. I hope
that maybe I can maybe give the word to Setafi Yusuf. Maybe he wants to advise and give some comments.
Thank you very much, dear Hisham, Professor Hisham.
sharing last, let's say, last conference, because after we changed the form of this initiative. So I will talk more about that in the end of this conference. So first of all, for me also, I would like to thank Dr. Surya to be here with us and to agree to animate this last conference. So I will give you the permission to share your presentation. So Dr. Surya, the floor is yours.
Hello. Is it audible and visible to everyone? Yusuf, can you hear me?
No, not yet. Just yeah. Okay. Okay.
Can you hear me?
It's okay now. Yes. It's okay now.
Yeah, great. Thank you, Yusuf and Hisham, both of you, for organizing this conference and inviting me. Thanks a lot for the kind introduction that you gave. So, welcome to all to my presentation on sensors for the environment and health monitoring. Thanks again for inviting me for the 16th e-conference at Mohammed VI Polytechnic University. As you all know, the environment surrounding us is getting contaminated with a lot of pollutants. The primary being the air pollution. So the major reason of the air pollution is the emanation of greenhouse gases. Various greenhouse gases include carbon dioxide, nitric base oxide, and sulfur dioxide. Similarly, we also have other kinds of air pollutions, which include gases like H2S and ammonia. Name it, there are many coming every day as new. The basic reason for the emanation of these gases are the industries that we operate and the automobiles that we use. Mostly NO2 and CO2 are emanated from the automobiles that we use and also the industries. The second being the water pollution. Water pollution is one primary hazard that's around us now because of chemicals that get dumped into the water bodies that we are surrounded with. This problem is still existential in most of the developing countries. Sometimes it so happens that the pharmaceutical industries, they just dump pharmaceutical residues and some chemicals that in fact cause a lot of pollution in the water bodies surrounding them. The third of these pollutions that I would like to cite is soil pollution. It has more or less similar activities as compared to the water pollution. People end up spreading these pharmaceutical residues and pesticides into the soil and they just forget. So it essentially leads to erosion of soil, because in soil we need certain kind of elements that are responsible for good crop output. So when someone spreads these kind of chemicals, they end up interacting with the soil salts and they degrade the soil, thereby causing the erosion. One often unrecognized hazard in the environment is the radiation. Radiation sources that include X-rays and gamma rays are quite are more or less like a pollutants which are invisible to us. Here, I would like to take you through some stats that were developed by Yole Development and IDTex. These two are the best analytic companies in terms of expecting or projecting any forecast related to the latest technologies. Yole Development in 2014 has come up with the total of around $564 million that were spent in 2014 on the gas sensors market alone. And further, IDTex has taken this a bit forward and they predicted the gas sensor market for environmental sensing is going to be around $3 billion by the year 2027. And if you see the orange portion within 2027, the highest is going to be for the portable air quality instruments. Not only the gas sensors, there is also good enough market existing for the biosensors. As you can see, from 2017 to 2023 forecast, the raise is more or less equal to 2 times, which is from $2.8 billion, it is going to be $6.1 billion. Let me correct this over here. This prediction was done before the COVID situation. As you see in the figure D, after the COVID, the need for microfluidic-based biosensors has shooted up a lot. The current predictions are by the year 2025, we will require around $10 billion worth. The market will be around $10 billion as opposed to $6.1 billion in 2023. And whereas it was in the figure D, if you see in 2023, it is predicted now around $8 billion. Thus, there is good enough scope for all of these environmental sensors to eventually work with. Here is the outline of my talk today. Initially, I will be talking about the objectives of my research that I have done so far and that I'm going to do in the future. The key components that are required for these environment-based sensors. And then the second thing will be the transduction elements that I'll be introducing and briefing a bit about different kinds of transduction elements that we use in our sensor activities. Followed by, I will be taking few applications as for the presentation over here, where these transduction elements are used. Towards the end, I will be discussing a bit about the sensing system requirement for the sensing systems and the applications. Objectives. So the main objective is to realize an ENOS, but it comes with a flow. So initially, we need to disrupt the sensing platforms. Since we are working on various environmental aspects, the sensing platforms will be changing and they need to be disrupted according to the application. Even before going there, the most important point is to identify the materials, sensing materials. One can identify sensing materials based on the application that we are going to use, and further, these sensing materials need to be deployed, or you said they need to be put on top of sensing platforms, which I would say as sensing devices, so that the extraction of the particular parameters during the sensing activity can be done easily. Finally, towards the end, in order to realize an ENOS, one requires a consortium of different elements like sensor arrays, the corresponding electronics to tune the signal and to get the data into required form. It can even involve digitization of the data, analog, because most of the sensors are in analog form. So you need to digitize them. And then the final aspect is to implement machine learning algorithms so that you can detect the sensor, the analyte that you are targeting with high amounts of accuracies. The key components involved in developing these sensors, irrespective of the application, includes the materials. The first being the materials. There are already a lot of materials like nanomaterials, nanoparticles, nanostructures, metal oxides, metal organic frameworks, and different types of organic macrocycles in existence to use for different sensor applications. The primary criteria for these sensor dongles should be high sensitivity, achievement of high sensitivity, high selectivity when compared to the other analytes. Your system has to use a very low power and it should be stable enough. Once you achieve these kind of parameters within your sensor, then the problem of optimization related to the deployment comes. It all depends on your needs. For example, in the statistics, I have shown you the orange part in the bar graph, which corresponds to deployment related to which is portable deployment. We can say it as handheld based sensing, but some of the applications doesn't require handheld based sensing. You may have a desktop based, wherein you have your instrument on the desk and that should suffice your purpose. Similarly, there are certain applications that require you to deploy the individual nodes of sensors everywhere around the city or in a specific place like a mine or oil rig. So the deployment can be taken care. So these are the three important key components that are involved while developing these sensor platforms. Yeah, coming to the transduction elements, the actual meaning of a transduction element is it's just a device that gathers the information from the physical world and transforms it into a meaningful signal. There are a lot of such transduction elements available. Here I am showing you around 4 transduction elements that have worked with, which from where I have experience. The first being the micro electromechanical sensors. Here what you see over here towards the left are the micro cantilever devices from where I started my actual research career. A cantilever device is nothing but a diving board in the swimming pool. It is basically hinged at one end and free to move at the other end. When you bring down the size, when you miniaturize the size of these diving boards to micron scale or nanoscale, they become MEMS-based cantilever and nano electromechanical based cantilever. So when you coat the surface of this with the receptor materials that are specific to your analytes, that are specific to your application, then they can be converted into good sensors, because these cantilevers, they are also made with materials like piezoresistors. When you have a certain deflection, it changes its, due to the interaction between the receptor material and the analyte, the deflection will tend to change the base resistance value of the device. On the Next, what you see is the quartz crystal microbalance. These are mostly disrupted in biological sensing as far as I've seen. So a quartz crystal microbalance is a device which consists of a quartz crystal plate that is sandwiched between 2 gold electrodes. There are people using with platinum electrodes too. The main activity of activating these kind of sensors is to immobilize or put your receptor layer over the top of these gold electrodes. The operation, it is completely based on frequency, the sensing activity here. When the cantilever is not loaded with any kind of receptor layer, it has a base frequency. Resonant frequency is what we call. Once you start loading the mass, depending upon the mass, the resonant frequency keeps shifting. So essentially, when you have a receptor layer and when you try to, when you send the analyte onto the system, when it starts binding with the analyte, due to the reaction, the mass also will increase. The increase in mass will essentially bring down your resonant frequency. That is how the transduction is done over here into the frequency. The third being the transistors. Transistors, as you all know, they're heavy. They're the basic building blocks of all the electronics around us, including laptops and mobile phones. It's a 3-terminal device. The device that I've shown you here shows gate, source, and drain. These are the 3 terminals, and it has one active channel layer. Most of the transistors in the mobiles have silicon itself as a semiconductor, and the advantages by using this kind of transduction element, it has multi-parametric possibility to study as a sensor. So those details will be explained in my next slides clearly with the applications. And here I would like to show you the last of the transduction elements, which is electrochemical sensor. An electrochemical sensor is again a transduction element that has 3 different electrode parts, just like the transistor, and they also have similarities in terms of extraction of the data, which are like, it has different types of voltammetric techniques from wherein you can get different kinds of data that you can further analyze during the sensing activity. So as I've explained before, the transduction element that you are going to use will always has its own advantage and unique feature. They can be decided upon the kind of application that you're going to use, and also based upon the ease of use in the application. First and foremost application that I would like to explain here is the pharmaceutical analyte detection. In this work, for the first time, we have used MIPS that are dedicated only for the pharmaceutical analyte called ciprofloxacin. Ciprofloxacin is an antibiotic that is often, as I've told you before, dumped in the water bodies in most of the developing countries by both the pharmaceuticals and sometimes even by the population who doesn't use them after getting the disease. So here, the main activity that we have done is to synthesize the chitosan gold nanoparticles based MIP, molecularly imprinted polymer, wherein the cavities, first I would like to explain the three polymer conditions that we have used over here. The first being the MIP adduct. MIP adduct is something wherein we have the ciprofloxacin already embedded into the polymer system, from where we will be extracting our receptor layer called molecularly imprinted polymer with the imprints, with the frameworks. That process of extracting MIP from the MIP adduct is called elution. For the process of elution, you need certain kind of solvents that readily extract the target analyte, here in this case SIP. And the third polymer, which is called as NIP, is just a chitosan based molecularly imprinted polymer that doesn't have any imprints, nor does it have any SIP inside. The measurement that I have shown here corresponds to MIP adduct and MIP. The MIP being the red, MIP adduct is shown in the form of red curve, and the black corresponds to the MIP after removing the SIP. This particular kind of measurement is called DPV, differential pulse voltammetry, where the reduction currents are read from the GCE electrode. Before going into the details, initially what I would like to show you is how we carried out the process of elution. In the process of elution, we tried with three different kind of solvents, one being methanol with acetic acid in certain ratio, and methanol with DI water and sodium hydroxide. Among the three, what we have figured it out through the through cyclic voltammetry that I've shown here in the figure A, and through the DPV, these are the measurements that we did after the process of elution. So from there, we identified that the highest current has been recorded for methanol and acetic acid combination, which essentially says the more number of ciprofloxacin has been removed from the MIP adduct, giving us the MIP. And the same in the bottom, the corresponding bar graphs show the same data in terms of oxidation current peaks and reduction current peaks for CV and DPV. So one can easily identify the highest current has been achieved for methanol and acetic acid here. Further, the surface morphological studies have been carried out between the molecularly imprinted polymer and non-molecularly imprinted polymer, the differences. Here one can easily see from the atomic force microscopy the highest peaks and valleys recorded for the MIP, but whereas in the case of MIP, we have seen very smooth surface as compared to MIP. Further, the confirmation has been done through the SEM images, wherein we have bigger peaks and valleys in the case of MIP over here, and more or less kind of same smooth surface. Here, the 2 micron is the resolution that has been utilized for both the SEM images. After the morphological study, we have continued with our studies of selectivity, sensitivity, and stability. In the first case, the selectivity has been done with other interference, as one can see from here, for both the MIP and NIP. So the other interference include uric acid, glucose, ascorbic acid, dopamine, and ciprofloxacin. And at the same time, we have used another antibiotics, which are like ciprofloxacin, which are called norfloxacin or orfloxacin. Among the all, we have received, we have seen the highest response for the ciprofloxacin as compared to the other interference. One may say here that from the figure, it is the response for the other analytes is not as much. It's more or less equivalent to the response got for SIP. Here, what I would like to suggest is we have repeated the experiments multiple times, and we achieved an error bar over here. Apart from doing this, we can also implement machine learning algorithm that takes care of each signature, thereby giving the highest accuracy. It can even identify, unlike the regular testing methods, it can even identify ciprofloxacin alone or uric acid alone or glucose alone from the training that it gets from the algorithm, from the code, sorry. Further going ahead, we did sensitivity studies that you see in the middle. We varied the concentration of ciprofloxacin from 1 micromolar to 100 micromolar. And we have seen a linear increase as per this reduction currents observed from the differential pulse voltammetry. The final being the stability performance experiments that we have done. Before even introducing any ciprofloxacin into the system for the detection, we swept the bias for around 100 cycles when the MIP is alone present on working electrode. Thus, we don't see any kind of deviation in its performance in terms of both oxidation currents and reduction currents. Finally, when you introduce the ciprofloxacin into the system, these current peaks tend to come down, identifying the CIP. Not only that, we have also conducted studies wherein we have mixed ciprofloxacin with the other interference that I have shown here in the before. Here, the experiments were conducted individually with individual analytes, but whereas here in this case, we have mixed the individual interference along with the CIP and we try to carry out. Except for the case of norfloxacin or floxacin, more or less, most of the responses were near about same and are more or less equivalent to the MIP alone kind of sensing result. But when it comes to norfloxacin and norfloxacin, we suspect that since they are also antibiotics, they tend to bring down the sensitivity to an averaged value, because as you see, the output is better than the individual outputs of norfloxacin and ciprofloxacin over here. This is the end of detection based on 3-electrode electrochemical system for pharmaceutical analyte. Going further ahead, as I told you before, my actual research career started with cantilevers, and that too on the explosive sensors. Explosives, as you know, are very dangerous and they're lethal. They take the lives of people and even it is dangerous to work with explosives and to inhale them also if you are even in the process of making them for some military cause. So the major reason for adopting this kind of sensor technology has some analogy related to our biological nose. As shown in the very first figure, in a human nose, inside the nostrils, one has olfactory bulbs that essentially interact with the analytes that we inhale. Olfactory bulbs are again connected through a neuronal path to the brain, which actually processes the information. The major reason for adopting this kind of inference from the biological nose is to come up with olfactory bulb kind of artificial sensor systems. These artificial sensor systems in the current case are cantilevers, but similarly in my future work, like in the work that I have done eventually used different types of artificial sensors that include OFETs and QCMs. The second block being the electronic system that takes care of your signal and properly digitizing it before it is fed to the brain. The brain here, in the case of electronic nose, are the neural networks and machine learning algorithms. They can be digitized or they can be analog-based algorithms that you can take the data and you decide about the analyte that you are detecting. In this case, it's explosives with certain amount of accuracy. So here in this case, what the transduction element, like I've explained before, used for the detection of explosives was cantilever. And I've even explained you the way working phenomena of cantilever. Essentially, as you can see over here in the right graph, you have the deflection on the x-axis and you have the change of the resistance happening on the y-axis. As the cantilever deflects, as it bends, there will be deflection in certain units of micrometers, and the corresponding change in resistance can be seen on the y-axis. This is recorded directly from the instrument by deliberately deflecting it with the tip of measurement unit. So after doing this physical analysis, we got into the cantilever. We got the cantilever to make them work for the explosives. The cantilevers were initially coated with coatings like 6-MNA and 4-MNA and 6-MBA. These are mercapto nicotinic acid and mercapto benzoic acid. that readily recognize RDX and TNT kind of explosives. So here in the figure, on one of the cantilevers, we have coated these with these receptor layers, but the other one is left here on the right is left without any coating, and it serves as a reference cantilever while doing the measurements. So this is the prototype finally that we have developed by making use of this cantilever system. The small tip over here that you see is the small flow cell that is exclusively developed only for pumping of gases into the system. And eventually, the change in the cantilever resistance is recorded and is converted to voltage, because the change in the current resistance is eventually converted to voltage and read as and is digitized to display on the LCD screen over here. The same flow cell with the cantilevers can also be disrupted for biological sensing if we can modulate the flow cell around it. Here, what you see on the right side on top of a green PCB is the same cantilever setup that is coated with antibodies and corresponding aptamers for biological applications that we have done previously. The two inlets that you see over here are to do the process of immobilization and to introduce the corresponding analytes into the system. Thus, the same platform can be used for both explosives and for also for the biological analyte detection. So the next phase of my work started, I deviated from the cantilevers and I got into transistors. Here, exclusively, I have used organic field effect transistors because the organic field effect transistors use the organic semiconductors as a channel layer. The advantage with the organic semiconductors is that they are biocompatible, and at the same time they have good enough functional groups within themselves to interact with the analytes that is coming in, unlike the other inorganic semiconductors. The other inorganic semiconductors, more or less, they need to be coated with receptor layers separately. But the advantage with organic semiconductors is that sometimes they can have their own functional groups, or the functional groups can be generated with certain processes. Or as you see in the third point over here, you can make use of composites with the organic semiconductors. That means if you have a receptor layer separately, you can make a composite out of both organic semiconductor and the receptor layer, or you can make stacks. There are also some challenges that were involved previously with the organic-based semiconductors because they were degrading at a faster rate. There were hardware-based analysis problems because not all OFETs behave the same like the inorganic transistors. There was lack of porosities in some kind of organic semiconductors. Porosity is really important in certain cases of sensing, and the reusability. Since they get easily degraded, they tend to fade away very easily also. So reusability was also a problem in OFETs. Here I have shown you the process of fabrication of an OFET. Initially, one requires a substrate, and on top of which we either put gate and gate dielectric, or in some cases, the substrate itself that you see over here can be used as the gate, depending upon the kind of substrate. If it is a highly n-doped or highly p-doped, you can use it as a gate electrode itself. After the step 2 of deposition of the dielectric that is required in the transistor, you can either go for the deposition of organic semiconductor or the deposition of metal deposition for the source and drain contacts. These two processes are interchangeable depending upon the geometry that you expect from the OFET. OFET geometry, there are 4 different OFET geometries, but most of the time we have used bottom gate, bottom contact, which means this metal deposition comes at the position 3, and bottom gate top contact, which means like initially you put the organic semiconductor and then you put source and drain contacts on the top. The final step can be deposition of the receptor layers if they exist, otherwise the sensing activity. For the sake of ease, I would like to show you a small animation that was done by one of our interns. Yeah. So considering that we have the substrate itself acting as the gate electrode for the transistor here, the first step is the highly doped silicon substrate, for example. What we do is the next process is the growth of oxygen. So the growth of oxide in the presence of oxygen. So silicon dioxide is grown, the second layer, through the process of dry oxidation. And then we go for the process of lithography, for which we require a thin photoresist layer, wherein you can illuminate some UV light in order to form specific brackets wherein you can come up with your contacts. Here is the mask in order to protect the photoresist from the illumination. And then you irradiate or illuminate the photoresist with the UV light. After this, the exposed part becomes hardened, and when you do the development process, the other parts gets removed from the photoresist and only the photoresist is left over there. This is useful because now you will go for the process of deposition of source and drain electrodes that I have explained before. Now that the source and drain electrodes are deposited, and when you do the process of lift off in order to remove the unnecessary part, you basically put the whole substrate into the acetone to do the process of lift off. The lift off process takes away the hardened photoresist. Now you are left with source and drain contacts that you see over here on the surface. And then you put your organic semiconductor on the top. Now that your device is ready, and this device is bottom gate, bottom contact configuration. So here the same bottom gate, bottom contact configuration is shown for the clarity. And the semiconductor that we are using here is a P-type semiconductor. This work has been adopted from Professor Horowitz. On the left, you have source. On the right, you have drain contact. In the bottom, what you see here is the gate, the silicon substrate itself. When you bias gate, the positive charge, the majority carriers in the P-type semiconductor starts getting accumulated near the channel region. That is the interface of the semiconductor and the insulator, sorry. And then when you start biasing it with the drain, now that the current starts flowing from source towards the drain, since it is P-type organic field effect transistor. So as you see in the animation, the current that is flowing at the interface is what we are interested in, and it is what helps us detect the analytes in the gas sensing activities or exploding activities. So the same P3HT based semiconductor has been used in the explosive detection process that I've shown here. This is the characterization setup. The device that you see over here in pink is the organic field effect transistor in the interdigitized format. This is a measurement probe station, and we have gas explosive generation unit over here. The small unit with with U tube over here is what contains the explosives or gas related materials. We just need to keep replacing this in order to pass on the gas into the system. This is very old setup. Currently, we do have a state-of-the-art setup, which I will be explaining soon. So we do the measurements of transistor. So there are two kinds of measurements that we can do from transistor. One is transfer characteristic based measurement, and others is output characteristic measurement. They have their own advantages in giving the extraction parameters from the sensors. So for this work in the explosive sensors, what we have used is composite based approach. As you see on the left, we have 4 different materials. They have been used to make into composites. P3HT being the organic semiconductor, it doesn't do any sensing activity directly over here. When you make composites out of P3HT, SXFA, copper tetraporphyrin, and ADB. SXFA is also another kind of polymer. This is a porphyrin, and ADB is a porous material. These composites have been made, and the corresponding activities that we have done and the output that we have got are also shown over here. Like P3HT and SXFA is very good in detecting both TNT and RDX, whereas the combination of PCS is good in detecting RDX alone. So before going ahead to these conclusions, what I would like to explain here is the measurements that were performed that I'm showing here on the right. The blue curves correspond to the extraction of the drain current in the transfer characteristics format from the device before exposure to any kind of explosive or non-explosive. And the red corresponds to the IDVG curve that we extracted after exposure. One can see there are different blue color curves and different red color curves within one graph. So they are extracted at different VDS levels, like I've shown you in the previous animation. As you keep increasing the drain voltage, you tend to get different levels of these IDVGS curves. The first figure that you see corresponds to TNT, and the second figure corresponds to RDX over here. From these characteristics, the advantage, like I've explained you before, from the transistors, you can do multi-parametric analysis. From these curves, we can extract different parameters, like the tip here over here gives you the on currents, the initial currents at the starting of 0 volts of gate bias gives you off currents. And apart from that, we can extract from these curves parameters like threshold voltage, sub-threshold swing, and transconductance. So we extracted, I'm unable to show you the complete data over here because you can imagine the 4 combinations with multiple analytes. There is humongous amount of data generated. Like you see over here, 127 OFETs were studied in this particular application. And after studying 127 OFETs, we extracted multiple amounts of data, which was fed into machine learning algorithms. Here, as you see in the middle, a tree kind of structure. This is where we have fed our data that we extracted from individual readings. S1, S2, and S3 being percentile delta I off, percentile delta I on current, off current, and transconductance that we extracted from 127 devices from these kind of characteristics. We fed those data into multiple machine learning algorithms. The J48 decision tree has been very successful. That's the reason that I'm showing you this particular decision tree output. So initially, the process starts by S2, which essentially means on current. If your on current value is greater than 10 power 3, 10.37, the algorithm will branch out towards the right direction, and it goes and looks for S1, which is essentially off current. If it is less than 10.37, it will again branch out and it will again look for percentile delta ion itself. So here the oval shapes are the uncertainties and rectangular shapes are the certainties, which essentially means when you arrive at a rectangular box, it is a certain value. If the rectangular box shows you 1, that means it's an explosive. If the rectangular box shows you 0, that means it's non-explosive. So this is how the branching out takes place. If you see the biggest branch out, it is from S2, S2, S3, S1, and S2. More or less, we have like 1, 2, 3, 4, 5, 6 branches to arrive at these values in order to confirm that if it's an explosive or non-explosive. This kind of, algorithms will be really useful when you have a data which is not very straightforward. Going further ahead, here we have explored explosive sensors with other types of OFETs also. Here I'm not going to show you all the characteristics that we extracted, but I would like to directly jump into the novelty in this work. Similarly, like before, we have realized one OFET sensor array with P3HT as organic semiconductor, but here in this case, we never formed any composites. We deposited a parylene C layer, the parylene structure that you see over here, on the top of the electrodes that is in contact with the P3HT. So further, what we did is parylene C was already explored at that point of time for opening up dangling bonds when you do the plasma etching on the top, and the contact angles were really high after the process of plasma etching, and the material readily becomes interactive and it starts interacting with different analytes. So we thought, why not use, apart from making a OFET, here in this case with the plasma etched OFET, it was detecting RDX and TNT without any problem. But further, we thought of studying the surface based parametric analysis, physical parametric analysis, by making use of Kelvin probe force microscopy. On the go, this is what we realized. We have the same stack that we used for the OFET, but on the top we have here plasma oxidized perylene. In the case of Kelvin probe force microscopy, we have the AFM cantilever tip that is, doing the scan over the surface, recording the surface potentials. On the right, what you see here is the measurements that were done with the AFM tip, KPFM tip. The first and foremost being the PC, which is perylene. We saw the surface potential coming around 400 millivolts, that is positive in the positive domain. The moment you do the plasma oxidation, as I've told you, it starts opening multiple dangling bonds of COO, C double bond O, C double bond C, because of which the contact potential difference or the surface potential tends to go towards negative, and it becomes around 600 millivolts kind of. This is the active material for our further studies, plasma oxidized perylene, which is called POPC. Further exposure of different analytes were done on top of POPC, and we have explored in this case multiple explosives and non-explosives. All of them, they started generating different signatures. Here, there is no specific selectivity for different analytes. If you see between TNT, RDX, benzoquinone and benzophenone, they are all towards the negative side, except for PETN. So PETN is another kind of plastic explosive that is often used in explosions. And here in this case, PETN was highly, this process was of measurement and the use of perylene C was highly selective towards PETN, and it always remained in the positive domain. The good thing about this PETN here is all the way from the negative side, the POPC has again moved towards the positive side at around 150 millivolts. So further studies were done to understand the quantitative and the quantitative based sensitivity, for which we have increased the concentrations of these explosives, TNT, RDX, and PETN that you see over here. Since these are materials with tremendous low vapor pressures, we need enough amount of temperature to increase the emanation of the molecules. So they were heated till up to 90 without any shock. We need to be careful. And the concentrations were increased to around 800 ppb. In the case of RDX, for PETN, it was around 120. So as one can see, as you increase the concentration from the KPFM analysis, the CPD values were also increasing linearly towards the end. So thus it comes to an end because this is a different OFET with different approach. This is another paper where we published in IEEE Sensors Journal. Excuse me. The next application where we used OFETs with different organic semiconductor, TIPS-Pentacene, which is also a P-type organic semiconductor, is in radiation sensing. As I have told you before, radiation is also one of the hazards that is present in the environment. Radiations like UV, X-ray, gamma, they are all present, including microwave radiations are also present everywhere. So among these, X-rays and gamma rays have the capability, they're just like electromagnetic waves that have the capability to remove electrons from the atoms. They can directly, So the problem when it comes to biological tissues, with these kind of ionizing radiations is the tissues, they will eventually die towards the end. And in case of inorganic things, like for example, electronic devices, there will be a performance degradation. So radiation effects are grave concern in different fields like space environment, nuclear applications, including electronic gadgets, I have told before. So here we thought of building some low radiation level device to estimate and to realize a sensor for radiation sensing. That's the reason we have used TIPS-Pentacene. TIPS-Pentacene has more or less tissue equivalent kind of material. People earlier used cadmium telluride and zinc telluride kind of materials, inorganic materials, and being in constant contact with those kind of materials is not that safe. So in this case, the tissue equivalent material like TIPS-Pentacene has been used. That's one advantage, apart from using the low cost approach of OFET. As you also know, like radiation therapy is also often used in cancer treatment, as it breaks down the DNA of the inside the cells, and thereby eventually causing the death of the cancer cells. For these, people use around 20 gray kind of dose levels on top on the patients suffering from cancer in the process of radiotherapy. Sometimes there are also units like rads and sieverts, but here essentially we are showing all of our study in gray. And the good human being or a normal human being will undergo an exposure limit of around 20 milligray per year when it comes to a gamma ray kind of exposure. There was a little tweak needed. Like I've shown you before, this is bottom gate, bottom contact structure. I'm not gonna repeat everything, but what I wanted to show you is how we deposited, because TIPS-Pentacene requires some SAM layer before you deposit the TIPS-Pentacene P-type semiconductor directly on top of the substrate we have. So the process involves plasma ashing to clean. This is more or less like cleaning with wet process also. And then we deposit SAM layers, which SAM are surface assembled monolayers that play a very good role in adhering the organic semiconductor to the dielectric present in the bottom. And then finally, we have realized the TIPS-Pentacene on the top. As I told you, this is bottom gate, bottom contact structure. The process recipe is shown over here. And yeah, in this case, the radiation was the gamma radiation that was generated was through cobalt-60 radiation source on top of OFETs. Most of the people who have done used OFETs or other kinds of FETs have claimed that most of the change in the response of the sensors is due to the irradiation, that means the exposure of the radiation that happens on top of the dielectric surface. Here we have taken two approaches. One, without irradiating any silicon dioxide, we deposited the TIPS-Pentacene, and then we exposed the gamma rays on top of TIPS-Pentacene material. And the second case being, before even putting any TIPS-Pentacene, we irradiated the silicon dioxide, and then on top of which we have deposited TIPS-Pentacene. These are the two different approaches that we took in this particular study to see the changes. As you can see from the KPM images over here, the Kelvin probe force microscopy of the TIPS-Pentacene material without any exposure shows around 1 volt, more or less, approximately 1 volt of surface potential. Whereas when it gets exposed through a minimal of 3 gray, it changes around, it comes down to 250 millivolts, which is around 1/4 of its initial value. This is the surface probing through the surface probing microscopy. The study has been done. But when it comes to the OFET, one can see the top, the signals that you have, the curves that you see over here are exposed to different radiation doses. For the silicon dioxide irradiated device on the top. But when it comes to TIPS-Pentacene irradiated device, one can clearly see that the threshold voltage has been shifted from for near about 5 volts kind of change from initial reading to a reading with 3 GY exposure. But whereas the threshold shift wasn't observed in the irradiated part, there we had change in threshold voltage, but it was really, really small. So this is attributed to the density. So the change in threshold voltage is mostly attributed to the generation of interface traps and bulk traps, especially from TIPS-Pentacene, and not just due to the generation of traps within the silicon dioxide. One can see on the right side the comparison of the mobility of the device in the TIPS-Pentacene irradiated device and dielectric irradiated device. In the case of TIPS-Pentacene, the initial first 1 gray has caused about 2 orders of change in the mobility, and then 1 more order till you reach 3 gray kind of dose. But whereas in the silicon dioxide irradiated device, you hardly tend to see one order change from 0 to 3 gray. Similarly, density of interface tabs has been calculated from the sub-threshold swing, the inset that I've shown here. So this is again, the green part corresponds to the TIPS-Pentacene irradiated and the pink corresponds to non-irradiated device. So by making use of sub-threshold swing, we calculated the density of interfacial traps, and again, you see the same change. Thus, essentially what we conclude from this study is it's not just the dielectrics that is more important in identifying the sensors related to radiation. It is also, there is crucial and important role of TIPS-Pentacene organic semiconductors in increasing the sensitivity of these devices. Next, I would like to jump into the gas sensors. Here, recently, before even coming to KAUST, I delved into working into gas sensors with OFETs and multiple devices. What I would like to initially show you here is the types of gas sensors that exist currently in the market. There are different types of metal oxide-based gas sensors, optical gas sensors, electrochemical gas sensors, capacitive-based gas sensors. All of these different types of gas sensors again use common transducers that we generally use, like interdigitated structure. This is disrupted for multiple applications, multiple types of transductions, like resistive transduction and capacitive transduction, including the transistor-based transduction. IDE is a transducer that is used over here. It just requires a little tweaking in the fabrication process. And fiber optics have been used a lot for gas sensing. Micromechanical systems of cantilevers were also used. I have shown you before. Quartz crystal microbalance and transistors, including the fluorescent stripes. When the gas analyte comes and interacts with the surface of stripe coated with the fluorescent material, there will be change in the intensity. That is how people identify. So in my case, I have used organic field effect transistors again, but here with a different approach as compared to my previous approaches. Earlier I've tried the organic semiconductor alone, or I made composites. Here in this case, we have used P3HT again as an organic semiconductor in combination with nanoparticles, metal oxide nanoparticles. That by this time that we carried out this work, tin oxide and zinc oxide were heavily explored, but there was no low-cost processes available to synthesize these materials through green synthesis process. So in this work, the receptor materials that are nanoparticles were made for the very first time using green synthesis method. That's the reason we had to do all kinds of material-specific characterizations. Here is a setup that I have shown you that we have used. It is more or less similar to what I have used before in the explosive sensing, wherein we had to change the YouTube. Here, H-trace has been generated through KIPS apparatus KIPS apparatus. In order to first realize that the materials that are provided, that are synthesized to green synthesis are indeed tin oxide and zinc oxide, we had to do XRD, UVs, and even EDAX. So from the XRD, the peaks corresponds to tin oxide in this case and the zinc oxide in this case. They are also really crystalline in nature. From the Scherer equation, we were able to estimate the crystallite size for tin oxide of around 29 nanometer and 16 nanometer for the zinc oxide. From the green synthesis process is what I'm saying. And we even did UV for these nanoparticles, and we extracted the band gaps of those materials just to confirm. So without going too much into the fabrication process and the way we have extracted these measurements through transfer and output characteristics, I am directly getting into the extracted data. Like I've told you before, the data that I've shown you here, the red bars correspond to data that I extracted using tin oxide OFET, and black corresponds to zinc oxide OFET. In the case of first figure, we have multiple parameters from the transistors like on currents, mobilities, saturation currents, and off currents. We all very well know that off currents of a transistor are very much susceptible to a lot of environmental changes. Thus, we couldn't really rely on them as they were inconsistent and were showing different high signatures to different kind of analyte. But if you see from the on currents, the mobility, and the saturation currents, one easily gets to know that tin oxide was really selective towards H2S as compared to zinc oxide, and it was also really selective among other analytes, interferons that we have used over here. Thus, we have further used the same tin oxide combination of P3HT OFET for other mining gases that include carbon dioxide, sulfur dioxide, and methane. So there also, what we have identified is H2S is highly selective. Sorry, tin oxide based OFET is highly selective towards H2S gas alone as compared to other materials in this case, like you can see. Another good advantage of this OFET that I have developed is its response time was very quick. It was responding within 20 seconds to reach the highest 90% maximum of the transient curve. Another application from the OFET is the NO2 gas detection. Earlier we did H2S. Here in this case we did detection of nitrogen dioxide gas. Here in the platform we have used again the bottom gate, bottom contact structure, but with a new new organic semiconducting material called PDBT10. When we did our initial performance analysis of PDBT10, we realized like it has the inbuilt functional units that can readily interact with NO2, causing the electron exchange over the surface with the PDBT10 organic semiconductor. Thus, we performed the analysis, and what we have realized is there is good enough selectivity of PDBT10 organic semiconductor as compared to the other oxidizing and reducing gases, but the amount of gas detection and the amount of change in the output characteristics and in transfer characteristics of these devices were very small. Thus, we had jumped into usage of another bilayer on top of PDBT10 organic semiconductor. Here we have used metal organic frameworks. For the first time, we used isostructural 3D fluorinated metal organic framework with porphyrin inside. If you remember, in my very first experiment related to explosives, we have used copper tetraporphyrin. There, the copper porphyrin were used as the receptor layer alone. Here, in this case, there is a synergistic combination of both MOF and porphyrin. So, wherein the porphyrin was made use as the organic ligand that is present in the structure of the MOF material. This is the new setup that I was telling you about. Unlike the previous setups, this is a state-of-the-art new setup that we use in our lab that I've shown you here. We have 5 different MFCs controlled to pass on different gases through different channels into the gas chamber that I've shown over here. This gas chamber can contain any kind of transduction element. In the previous case, we made the gas chamber so that we can use only OFETs, but this particular gas chamber has capability to accommodate different gas transduction elements like QCMs, capacitive sensors, transistors, and even optical fibers. These are the complete parameter extractions that we have done using the OFETs in this case. So like I have explained you before, the addition of MOF onto the structure of OFET with PDBT10, it not only increased the selectivity with respect to other interferons like H2S and ammonia, but it also increased the sensitivity more or less like 6 orders more than PDBT10 device alone. The corresponding graphs that we show here are for different concentrations of the NO2 exposed. Here what you see is the drain saturation current, and in this case it's the on current change and along with the shift in the threshold voltage in the transfer characteristics. Here the same is depicted with multiple parameters in these two images. The left being the threshold voltage, the threshold voltage is going down over here with the increase in the concentration of the NO2 gas. Similarly, the red curve corresponds to the mobility. Also, one can see the ion by IOF ratio on the left here, and subthreshold swing changes over here. The device that I've shown you here, the transient analysis is shown over here. It makes sure, like, it is to show that the device can revive at different concentration levels and it can be reused. So this is one short run of transient analysis. The figure that you see over here corresponds to this figure collected over a period of 200 days. With every 10 days gap, we did performance analysis of the device, and the device response seems to be quite stable over a period of 200 days, saying that this doesn't require any changes in the organic semiconductor in order to activate the surface. So the final application that I would like to explain in my talk today is the single wall carbon nanotube based cardiac marker detector. So the cardiac marker detection is done with the help of not only just the single wall carbon nanotubes, but also we used cobalt oxide nanorods in this case as an active element over the surface of single wall carbon nanotubes. The first thing that I would like to explain is AMI. AMI is acute myocardial infarction. That is a condition of a heart attack. This condition can be recognized in two ways. Either you do the ECG or you do the plasma extraction, from where you try to see the proteins present in the plasma. So when you have the presence of these different proteins like troponin T, myoglobin, and fatty acid, these are the most abundant proteins that gets released, apart from troponin I and creatine-based protein. So we have used here, we have exclusively targeted the detection of troponin T in this work. Going further ahead, we have used the same approach of silicon dioxide substrate, but wherein on top of interdigitated electrodes, we have the active channel of silicon single wall carbon nanotubes over here first. And then there are another two more approaches of deposition. First, we deposited cobalt oxide nanorods to understand the sensitivity aspects of the sensor device. And then followed by that, we also deposited with gold nanoparticle loaded cobalt oxide nanorods. Once we have prepared the device, we immobilize the surface. This control study corresponds to single wall carbon nanotubes alone and the detection process. Here in this, what I have shown you is the corresponding response of the signal with respect to gold loaded cobalt oxide nanorods on top of single wall carbon nanotubes. So the figure that I've shown you here can give better better analogy. So you have the nanorods deposited over here on top of single wall carbon nanotubes, and then the bubbling that you see around here is what happens when you do the process of immobilization. Initially, we have put streptavidin to form a very good binding, and then on top, after 5 minutes, we have drop casted the concerned aptamer, DNA aptamer, that is related to troponin T on top of the streptavidin. This is the primary receptor or binding element that is required. And thereafter, we have done the deposition process of, drop casting process of various proteins. So among the different proteins that we have deposited to check the selectivity are troponin T, myoglobin, dopamine, and glucose. And one more is ascorbic acid. Yeah. So among all the five, what we have realized is the device is highly sensitive towards troponin T. And among the three different types of receptor layers that we have deposited, carbon nanotubes had very minimal change as compared to the cobalt oxide nanorods. And as compared to gold loaded cobalt oxide nanorods, what we have seen is cobalt oxide gold loaded cobalt oxide nanorods had really very good sensitivity as compared to the gold cobalt oxide nanorods alone. And apart from that, we have also made a study how much amount of gold loading on top of cobalt oxide nanorods is important in order to come up with very precise optimized value of sensitivity. So here what you see is the requirement is around 1 ml of gold loading on top of cobalt oxide nanorod solution will give proper and high sensitivity when it comes to detection of troponin T. So by this, I am done with explaining different types of transduction elements and applications that we have realized over the time. So towards the end, we were also working on developing different types of prototypes. So this is the first version of our prototype that we have made, wherein we made use of capacitive sensor device that you see over here, which is coated with metal organic frameworks. One
5 minutes, Dr. Surya. We have still.
I'm almost done. Yes, I'm almost done. Thank you very much. So one corresponds to the device that is coated with metal organic frameworks and that is exposed. The other reference element, the transduction element, is non-exposed metal organic framework deposited device. So we built this device wherein we can convert the capacitance values to voltage by making use of AD7746 chip. Essentially, this particular chip has a capability of converting the capacitance values of certain range in the range of 1 picofarad to 50 picofarad, if I remember correctly. So within that range, if there are any fluctuations from the baseline capacitance, it will be easily identifying the changes and it will eventually send it to the computer over here. But as the research has gone forward, we were able to successfully make, this was the envisioned thing, but we were able to successfully finish this prototype, wherein we have a small motor, DC motor, that acts as a suction pump to gather the air surrounding, because once you have a handheld system or a portable system, you need to go around and suck the air into the system to do the process of analysis. So that particular pump takes the air and puts onto the IDE chip for the detection process to happen. And if the particular analyte reaction happens with the receptor material present over there, there will be change in the capacitance, eventually leading to change in capacitance over here. The final prototype that we realized towards the end was this. It's the same DC motor suction pump. We have an inlet and outlet. We have the flow cell over here with the sensor, transduction sensor element over here. It passes on the gas and it outlets. And what we can see here is like we have the LED based indication with also the LCD on the top. It doesn't only show you the values or indicate the presence of analytes, but it can also wirelessly transmit to the database through IoT module that is embedded inside the PCB. So from version 2 to version 4, what we have claimed is like we went really towards green. We reduced the current consumption. When the DC motor is turned on, it consumes around 110 milliamps, but more or less you never need the continuous operation of the motor. You just suck the air and the rest of the process can be done with the electronics alone. So it consumes really less as compared to the previous versions. 44 milliamps is what it consumes on the overall. What we are further trying to do is like realize, instead of using the electronics that we have shown you before, make use of the OFETs itself, wherein you have the sensor over here and similar OFET, but with encapsulation. By means of this configuration, you digitize everything, and wherein you can show different levels of gas concentrations. What you see here over here is the increment in gas concentration, and once you see the bottom, what you see is the digitized values. So the moment you have 1 ppm, it shows you all ones in a 5-bit code, thermometer code, but at 0 ppb, what you get to see is all zeros in a 5-bit thermometer code. It all depends on the current that is developed within this transistor element when you increase the concentration. And similarly, the difference in the currents that is generated from by varying the VGS over here, tends to change the voltage input of the inverter. Thereby, you end up realizing this kind of thermometal code. So the main use of this particular IC configuration is to get rid of the previous electronics that I have been showing here, and finally you will have only the reading part, which is digitized part, directly being displayed. So most of the electronics can be get rid of, and you can further bring down the current levels to microamps kind of range. That's it. We have the collaborators all around the world, including Morocco. What I would like to suggest at the end of this presentation is plant trees, because they are not there just to absorb carbon dioxide. Recently, the research says they can even, the leaves of the plant or trees, they even absorb particulate matters and other volatile organic compounds too. I would like to acknowledge my team. Here is my current supervisor, Professor Khalid Salama. He's the director of Sensors Initiative, and my previous PhD supervisor, Professor Ram Gopal Rao. And here is my team. I would like to thank one and all for their support. Thank you. Thank you very much. And yeah, I'm open to questions. Hi, Yusuf.
Thank you very much, Dr. Surya.
I hope I didn't take a lot of time.
I pass the floor to our chairman, Professor Hisham bin Yusuf, please. The floor is yours. Professor Hisham. Professor Hisham.
Please unmute. It's muted. Yes.
Okay. Do you hear me now?
Yes.
Okay. Thank you, Dr. Surya, for the nice presentation and really a large overview of, let's say, a lot of sensors types, going from NOx to other, let's say, type using MOFs, hydrazine, microcycles. I have seen also modified thiophenes. Before maybe starting, let's say, the session of questions, I don't know if there are a lot of questions. I will start this session of questions. And I have really one related to really the chemicals or the materials you are using. And when I see all these type of materials, either MOFs, metal organic frameworks, and so on, all of them are having, let's say, controlled morphology or porosity, let's say, to be specific.
Yes.
Now, how does this, let's say, porosity plays a role on the sensing, let's say?
So okay. So essentially, the porous materials makes sure, in the case of composites, these porous materials also have functional groups inside the receptor layers. So the moment the analyte comes in, these porous materials make sure that the analyte molecules, they go into the surface, into the bulk of the material. If the receptor layer, like MOF or hydrozones or macrocycles, if they themselves are the receptor layers, there will be a change induced into the readings of the sensor itself. If it doesn't, there is another aspect of this porosity here. The porous material will make sure it will pre-concentrate the analytes, and the process of interaction will be taken care by the layer that is beneath this porous material. I hope I'm making sense. Pores make sure that it goes in, but the actual activity happens over the interface of the porous material and your active channel material. So there are two ways of interpreting that porous nature coming into picture.
Maybe for the let's say the next, let's say, questions, I don't know, Sius, you have other questions or people asking questions?
Very much, dear Hisham. So if you give me the permission, I will manage this part of the question and answer.
Yes, please. Yes. Before that, I would like just to. Yes, I will give you just. I would like really to Surya for this nice presentation. As I said, it was very important.
Thank you, Hisham. Thank
I
you.
will back to you. I will back to you. Thank you. So
okay,
just I would thank Dr. Surya for this excellent and really I'm geologist, so for me this is a new information that I get this afternoon. So I want to share with our two important points, if you want. So the first one is, as you can see, here in our weekly conference initiative, so we're trying to share some important knowledge which are shared by our speakers, and I think this is the very important things that we can win in this initiative. The second point is that I apologize for the attendees that asked me for the attendee certificates. So because as you know, this is a volunteer initiative, so we're using currently some traditional, if you want, traditional manner to elaborate the certificates. So it takes some time to be ready to send to you. So we will receive it if you have the score mentioned in the beginning of each conference. So for the questions, so I will start by my friend Abdullah Ihsan. So please, if you can present yourself and if you have a comment or questions. So please,
Thanks a lot. Can you hear me, please? Please confirm.
yes, go ahead.
Thank you. Thank you, Dr. Yusuf, and thank you, Dr. Hisham. I would like, first of all, before talking about, the scientific content of the presentation of my colleague, Dr. Sandeep Surya, I will talk a part of his experience. I will talk about he's a very nice person. Actually, when I joined KAUST last year as a postdoc, he was providing all the help. He's a very nice person. Actually, he helped me a lot to join this endeavor. I would like actually to take this opportunity to thank him for all of things that he has done for me. Thank you so much, Dr. Sandeep. So as we have seen actually in the presentation or the talk of Dr. Sandeep, he has taken us to this long journey of sensors. He showed in his presentation different kind of applications, from pharmaceutical analysis to biological sensors to explosive sensors to gas sensors, all of kind of sensors. He's doing actually a great job, and we are working together actually in many other projects, including the use of metal organic frameworks, the use of the molecularly imprinting polymers, which is actually a promising field to develop new generation of sensors to get, and also we are trying to develop new flexible sensors for health monitoring, for environmental monitoring, as well as for food safety. I have just one comment for Dr. Sandeep to develop such kind of sensors, especially for gas sensing, because he's actually expert in gas sensing. What are the parameters, the critical parameters that we need to take into consideration before, moving to this step? Thank you so much.
Thank you very much, Dr.
Thank you, Dr.
So we're trying.
Thank you, Latif. Thank you very much for your kind words. And coming to your question, when it comes to gas sensors, it always depends on the material that you are going to use. Like I've explained before, while I was discussing with Hisham, if there are multiple parameters that really need to be tweaked. Like if you're targeting one particular transduction element, you need to tune down all your material-based, deposition-based activities according to the transduction element that we are going to use. If, for example, in case of transistors, you need to also have one semiconducting material, be it the receptor layer itself or an additional layer that you're going to put on top of the active channel layer. So these kind of things need to be taken care. If you can take care of these things for individual transduction elements, and if you can tune, there is also requirement. Like in one of the examples that I've shown you, initially the NO2 sensor wasn't that much sensitive enough for the PDBT10 OFET. But the moment we brought the MOF into picture, it increased the it increased the pre-concentration of analytes, and it made the NO2 to interact, the more number of NO2 molecules to interact with the surface organic semiconductor. So these kind of individual tweaking is very important. This is what I feel in order to make good gas sensors. Yusuf.
Okay, thank you very much. Well, I think that we can take the questions in the Q&A option, please, Dr. Surya.
Yeah.
So I think that we have here some four questions, because so we'll try to be fast because we don't have enough time. Just we have 10 minutes to closing the session, please. So you can read
Q&A. I cannot find any.
Okay, so I can read for you.
Yeah.
I will take the question of Mr. Ali Gullerbach, which he said, what is the sensitivity and the cost of different sensors presented? Is there any sensor to measure heavy metals in the environment samples? Is there sensors which are specific for each metal, for example, cadmium and lead?
So as I've shown you before, the sensitivity aspect comes into picture when you have different amounts of, it always depends on the concentration of the analyte that you're going to expose. And yes, we do have heavy metal sensors, but as of now, we are not currently working in that particular aspect. But soon, yes, as Mr. Latif said, Dr. Latif said, we'll be soon working in heavy metal based detection soon.
Okay. So we have here another question from Salahuddin Al-Karwani, who said how the sensors can be used in machine learning.
Sorry, can you please repeat how the sensors can?
How the sensors can be used in the machine learning.
Yeah. So see, that's what I explained. When it comes to the ciprofloxacin experiment that we did, I told you, like most of the people, when they see that your interference signal is more or less approaching the signal of your actual analyte, they tend to think like the sensor is waste. This is where the machine learning comes into picture. And apart from that, it also gives you a multi-dimensional, aspect. Though you know that your particular data isn't that much suitable to accurately say that this particular analyte is of so much accuracy, by means of machine learning algorithms, when you input this much amount of data, you can come up with higher accuracies. When you implement those algorithms, you can eventually come up with higher accuracy when compared to the regular way of looking at the data in identifying the analytes.
Yeah. So I will take Madame Lubna Fils. Please present yourself and question briefly. Thank you.
Thank you, Monsieur Daffy. Hi, everybody. First of all, I'm so delighted to attend again at this conference, and a special thanks will be driven for Dr. Surya for her presentations. So my questions will about, you talk about the built sensor, nanoparticle, metals, etc. So these products are known as hazardous materials. So thereafter, we proposed a new technology, so that is promising, fascinating technologies. How we can, but the missing part is how we can get rid of this promising technologies. Have you ever thought of promising method to mitigate the risks after the dysfunctional of equipment? Thank you so much.
Thank you very much.
If you don't mind, it wasn't that much clear. What was the question? Is it on metal oxide metals? Can you please?
Yusuf,
yes.
Just my question about, we proposed a new promising technology is fascinating, but the content of this equipment, as you proposed by nanoparticle, metals, etc. But after the dysfunctionments, when we could get rid of this dysfunction, will we get rid in the environment? So this material may be act as a vector to bring some pollutions. And this kind of pollution could disrupt the environment, biological systems, and some several living area will be in upset. So how we can get right? Okay.
So, thanks a lot.
The toxicity, I think.
Yeah, toxicity. Yes, most of the time you are not going to dump these sensors. Most of the time, this is my experience. I've been working a lot. So there are ways to reactivate the sensing elements. So there is possibility of reactivation. So you can, so that you can, you go again and you reuse them, or else you so even what I feel is like the remaining 10% of the applications, they should be research happening so that this kind of toxic wastage won't be there for much. But what from my experience, unlike the most of the other researches where people use lead based things, for example, a lot of people know, like recently perovskites have been implementing a lot of lead-based wastage is going into that perovskite-based solar cells. So unlike those kind of applications, the amount of usage of these metal-based or metal-based receptor layers are very less in sensor domain. That is what I feel. I mean, like people are going towards more organics and more organics-based sensing activities.
Okay, so I will take another questions from Saeed Al-Hanafi. He said, "Thank you for your presentation. Can we use this protocol to detect CH4 emission gas in the station of methane production?"
Yeah, definitely. By tweaking the receptor layer for the particular CH4 analyte, these platforms, more or less everything, all of these transduction elements can definitely be used in detecting CH4. Only thing is that you need a tweak in the receptor layers.
So we have also the second question from our friend Ali Boulerbah. He said, "What do you think about biological sensor? Did you have some data on this kind of sensors?"
Sorry, what is the last part? Did you?
What do you think about biological sensor? And he said also, did you have some data on this kind of sensors?
Yes, we do have the work that I've shown you related to troponin T based, troponin T sensing by making use of single wall carbon nanotubes is related to biological sensing, right?
So I have another question from Fatima Zahra Salih. So please, what are the properties of C3O4 nanodes exploited in the case of SWCNT cardiac marker detection?
Oh, okay. So it has multiple properties. Like if you see the cobalt oxide nanorods used in this case were P-type cobalt oxide nanorods. So essentially, there is this exchange of holes, depletion of electrons. When you have this gold coated onto it, the gold tries to pull over more number of electrons, making it more P-type. And this making of more P-type will eventually had effect on the single wall carbon nanotubes. Yes, these are the properties that are considered before getting into usage of cobalt oxide nanorods for the particular application.
Okay, great. So I will take the last question from Fatima Zahra Al-Hilali. We say good afternoon. Good afternoon. So thank you for initiative and efforts. So could you please tell me if you can put smart sensors with the composite material in a brack system to improve the performance of bracking?
Sorry, Yusuf, there was some disconnection. It wasn't.
I repeat again.
Yeah.
She said, "Good afternoon. Thank you for your initiative and efforts. So could you please tell me if you can put smart sensors with composite material in a brack system to improve the performance of bracking?"
Which system? Bat system.
Bracking, yeah, brack system. I don't know what it means, but she said that this is, I think, that's a technical word.
Yeah, Brad. I can't even hear what is that word actually that you are using. Hello.
So she said braking system. Braking system. Talk about the performance of braking system.
Sorry, I give up on this question. I cannot hear.
I will try to send you.
Yeah, please.
How can I do that? No. So I will put it in the chat.
Recyclability.
In chat, can you see the
okay.
yeah.
Okay, good afternoon. Good afternoon. Thank you for your initiative and efforts. Could you please tell me if we can put smart sensors with composite material in a brake system to improve the performance? Yes, definitely. So the composite can be of piezo resistive nature, and the moment you apply the brake, yes, definitely it works there. Yeah, I agree with you.
It was our last question, and before closing, I would like to thank our partner and sponsor, University Mohammed VI Polytechnic, for the help and for the promotion of this initiative. I also would like to thank the organizing committee, who did not spare effort for the success of this initiative, which started since 1st April, and who wanted to transform our confinement days into a learning and training opportunity at home. So I thank also the administrators of the Moroccan researchers group in Facebook, and also my colleagues in Geology Media Group. And finally, I want to thank a lot the international network ForestNet. We will not be around in coming back with a new initiative. The experience has pleased us, and a lot too. So we intend to continue, but with this time with the slower pace, because we know very well that after implement, each of us will have other occupations. So I wish you very good continuation, and do not forget to join our network to follow our news and our events. So, dear Chairman, the floor is yours for closing of the session.
Well, thank you, Sirius. In my turn, it will be my great pleasure to really thank the Mohammed VI Polytechnic University for the support. Of course, all the organizing community of this e-conference. It was really a success. The number of audience, the interest, and also and especially the multidisciplinarity of the conferences. It was really waving from different topics, different fields, and it's always has been great to hear really people talking about their patients. You are not in the field, but you hear them talking about their field in really great manner, and they are really having really let's say as we say the touch and the punch to say, we like this and we go for it. And it was really a real pleasure to hear them. The organizing committee, they are doing a lot of job in the back scene. They are not visible, but really they are taking care of all the logistics and so on. I am really, let's say, in the emailing, and I see really a lot of people really doing a great job. I know that they are very busy, and then it was really a great pleasure really to support at least from the scientific part as a part of the scientific committee. Just also, it will be really the moment really to thank now, after all the let's say the acknowledgements from Sirius, let's say the geology union and all these colleagues which are, let's say, supporting this initiative. And to not take too much time, I would like now to thank Dr. Surya for his excellent presentation. It was really a great presentation in terms of really flying around the different type of sensors, different technologies. I have seen lithography, imprinting, nanoprinting, really interdigitated electrodes, type and sensors and so on. I had a lot of questions, but I left the floor to the others because we can share it afterwards. We can share some let's say some emailing and so on, and it will be great pleasure to maybe to collaborate in near future. I will give back, let's say, the word for closing for my dear Yusuf to close the session.
To the Dr. Surya, maybe to ask.
Yeah, thanks.
Yes.
Yes.
Yeah. Thank you very much. I have seen one more question. There was this question about what about the future of phosphate-based OFETs? So I just answered I think Driss Fadili. So yes, there is the phosphate is really important, material. It's an important component in soil monitoring. So we are exploring the usage of OFETs in phosphate detection. So I just answered it. And apart from that, I would like to really thank Yusuf and Hisham, both of you, for continuously, making this possible. I really enjoyed it. Thanks a lot. Thanks a lot to both of you, including Mohammed VI University, Polytechnic University. Thanks a lot for all the organizing committee. Thanks a lot.
Thank you. So ciao, ciao.
Ciao, ciao.